Subscribe to the channel so you don't miss out on any of these videos. Space is vast, mysterious, and brimming with secrets we've barely begun to uncover. But imagine this, an invisible web of intergalactic matter, stretching across the universe, quietly holding clues about the cosmos' structure, evolution, and hidden past. What if we had a way to map it? A hidden code etched in the light from ancient quasars, a cosmic forest that acts as a blueprint of the universe. This is the story of the Lyman Alpha Forest, a term that might sound obscure but holds the key to unlocking some of the universe's most profound mysteries. Now, before we dive into the science, let me ask you something. When you look up at the night sky, you see stars, maybe a faint glow of the Milky Way, and if you're lucky, the glimmer of a planet or two. But what if I told you that the space between those stars, what seems like an empty void, isn't empty at all? In fact, it's teeming with matter. It's a silent, invisible network of hydrogen gas that not only exists but holds a detailed map of the cosmos itself. And we've discovered this map using light from the most distant objects in the universe, quasars. Intrigued yet? Let's explore this hidden map in detail. The story of the Lyman Alpha Forest begins with hydrogen, the simplest and most abundant element in the universe. Nearly everything we know about the cosmos' earliest moments comes from hydrogen. After the Big Bang, the universe was mostly hydrogen and helium, forming the foundation for everything we see today. But hydrogen doesn't just sit there quietly, it absorbs light at specific wavelengths, and this property is what makes the Lyman Alpha Forest so special. When light from a quasar, one of the brightest and most energetic objects in the universe, travels billions of light years to reach us, it passes through clouds of hydrogen gas scattered across the universe. Each cloud leaves its mark on the quasar's light by absorbing a specific wavelength. These marks show up as dark lines on the light spectrum, forming what scientists call the Lyman Alpha Forest. The forest refers to the dense collection of these absorption lines, each corresponding to a different hydrogen cloud the light has passed through. Think of it as a breadcrumb trail left by intergalactic matter, giving us a way to trace its distribution across the universe. Here's where it gets even more fascinating. These absorption lines don't just tell us where the hydrogen is. They also carry information about the conditions of the early universe. The further away a quasar is, the older the light we're observing, because that light has taken billions of years to reach us. This means the Lyman Alpha Forest isn't just a map of space. It's a time machine, showing us what the universe looked like at different stages of its life. But how does this map work exactly? Let's break it down. Each hydrogen cloud absorbs light at the Lyman alpha wavelength of 121.6 nanometers. However, because the universe is expanding, the light from distant quasars gets stretched out, or redshifted, as it travels toward us. This redshift means that the absorption lines we see in the spectrum aren't all at 121.6 nanometers. They're spread out across a range of wavelengths, depending on how far away each hydrogen cloud is. By studying these redshifts, astronomers can figure out the distance to each cloud and create a 3D map of intergalactic hydrogen. This map isn't just a cool visual, it's a powerful tool for understanding the universe's structure. The distribution of hydrogen gas traces the cosmic web, a vast network of filaments and voids that make up the large-scale structure of the universe. Galaxies form along these filaments, like dew collecting on a spider's web, and the voids in between are almost completely empty. By mapping the Lyman Alpha Forest, scientists can study how matter is distributed on the largest scales and how it evolved over billions of years. But the Lyman Alpha Forest doesn't just tell us about structure. It also holds clues about dark matter and dark energy, the mysterious forces shaping the universe. Dark matter, which makes up most of the universe's mass, doesn't emit or absorb light, so we can't see it directly. But its gravitational pull affects the distribution of hydrogen gas, leaving an imprint on the Lyman Alpha Forest. By analyzing these imprints, scientists can learn about the properties of dark matter and how it influences the cosmos. Dark energy, the force driving the universe's accelerated expansion, also leaves its mark on the forest. By comparing the distribution of hydrogen at different times, astronomers can measure how the expansion rate has changed over time, providing critical insights into the nature of dark energy. In this way, the Lyman alpha forest acts as a bridge, connecting the visible universe to its invisible components. So, how do astronomers study the Lyman alpha forest? The process starts with quasars. These incredibly bright objects are powered by supermassive black holes at the centers of distant galaxies. As matter falls into the black hole, it heats up and emits light across the spectrum, making quasars visible from billions of light years away. This light serves as a beacon, illuminating the hydrogen clouds it passes through on its journey to Earth. Using powerful telescopes, astronomers collect this light and analyze its spectrum. The dark absorption lines in the spectrum reveal the presence of hydrogen, while their spacing and intensity provide information about the cloud's density, temperature, and composition. Advanced computer models are then used to piece together the data, creating detailed maps of the universe's large-scale structure. One of the most exciting discoveries enabled by the Lyman alpha forest is the detection of the intergalactic medium, or IgM. This vast reservoir of hydrogen gas fills the space between galaxies, acting as a cosmic scaffolding for galaxy formation. The IgM is incredibly diffuse, so much so that it's invisible to the naked eye and even most telescopes. But through the Lyman alpha forest, we can study it in unprecedented detail, unlocking secrets about the universe's early history and evolution. The Lyman alpha forest has also played a crucial role in understanding reionization, a major phase in cosmic history. After the Big Bang, the universe was initially hot and ionized, but it quickly cooled, allowing neutral hydrogen to form. This neutral hydrogen filled the universe during what's known as the Dark Ages, a period before the first stars and galaxies lit up the cosmos. As these early stars and galaxies formed, they emitted high-energy radiation that reionized the hydrogen, marking the end of the Dark Ages. By studying the Lyman alpha forest, scientists can pinpoint when and how this reionization occurred, shedding light on one of the universe's most transformative eras. This transformative era of reionization is one of the most captivating chapters in the story of our universe. To truly grasp its significance, imagine a universe cloaked in darkness, where neutral hydrogen absorbs almost all radiation. This era was like a cosmic fog that enveloped the universe. But then, the first stars and galaxies ignited, their intense radiation breaking apart hydrogen atoms and creating a universe bathed in light. This transition from darkness to light didn't happen all at once. It was a gradual, complex process that left imprints visible today in the Lyman alpha forest. The absorption lines in the forest help scientists pinpoint when and where reionization happened. By comparing the spectra of different quasars, astronomers can observe the evolution of the forest over time. When the universe was still mostly neutral, the forest's absorption lines were dense and continuous. As reionization progressed, gaps began to appear in the forest, representing regions where hydrogen had been ionized. These gaps grew larger over time, painting a picture of how the cosmic fog lifted. One of the most groundbreaking uses of the Lyman alpha forest in studying reionization involves mapping bubbles of ionized hydrogen. During reionization, galaxies and quasars acted like lighthouses, emitting radiation that carved out these bubbles in the surrounding neutral hydrogen. The size and distribution of these bubbles provide vital clues about the properties of early galaxies and quasars. For instance, larger bubbles suggest more energetic sources or clusters of galaxies working together to ionize the hydrogen around them. But studying reionization isn't just about looking back in time. It also helps us understand the conditions that allowed galaxies like our Milky Way to form. The process of reionization heated the intergalactic medium, preventing small, low-mass galaxies from forming. This suppression of galaxy formation shaped the universe's structure and explains why we see the patterns of galaxies and voids that we do today. The Lyman alpha forest has also been instrumental in testing and refining cosmological models. By comparing the observed forest with predictions from simulations, scientists can evaluate how well their models describe the universe. These simulations incorporate physics on a massive scale, from the behavior of dark matter to the influence of gravity and the expansion of the universe. When the data from the Lyman alpha forest aligns with these models, it confirms our understanding of the fundamental forces shaping the cosmos. When it doesn't, it points to gaps in our knowledge, sparking new avenues of research. One such gap involves the small-scale structure of the universe. While the cosmic microwave background radiation gives us a snapshot of the universe shortly after the Big Bang, the Lyman alpha forest provides a complementary view of the universe's large-scale structure over billions of years. By comparing these two datasets, scientists can test the Standard Model of Cosmology, which describes the universe's composition and evolution. Discrepancies between the two could hint at new physics, such as interactions between dark matter particles or variations in the properties of dark energy. The Lyman alpha forest also helps scientists investigate the mysterious phenomenon of warm dark matter. While dark matter is usually thought to be cold, meaning it moves slowly in clumps together to form the scaffolding for galaxies, some theories propose that dark matter could be warm, moving faster and smoothing out small-scale structures. The distribution of absorption lines in the Lyman alpha forest can distinguish between these scenarios, providing critical insights into the nature of dark matter. And then there's the tantalizing connection between the Lyman alpha forest and black holes. Quasars, the light sources for the forest, are powered by supermassive black holes. The intense radiation from these black holes illuminates the surrounding hydrogen, creating the absorption lines we study. But quasars also leave their own imprints on the forest. As a quasar's energy ionizes the hydrogen around it, it creates what scientists call a proximity zone, a region where the absorption lines are less dense because the hydrogen has been cleared out. By studying these zones, researchers can learn about the quasar's luminosity, age, and even the environment of the black hole powering it. The interplay between quasars, black holes, and the Lyman alpha forest opens up fascinating questions about how galaxies and their central black holes co-evolve. For example, do supermassive black holes regulate the growth of galaxies by emitting energy that heats and expels gas, preventing star formation? Or do galaxies feed their black holes by funneling gas toward their centers? The patterns in the Lyman alpha forest offer clues to these questions, helping us piece together the intricate dance between matter, energy, and gravity in the universe. Another exciting avenue of research involves using the Lyman alpha forest to measure the universe's expansion rate. The forest's redshifted absorption lines provide a detailed record of how light stretches as the universe expands. By analyzing these patterns, scientists can calculate the expansion rate at different times in the universe's history. This information is crucial for understanding dark energy, which is thought to drive the universe's accelerated expansion. Any deviations from expected patterns could reveal new physics, challenging our current theories about the universe's fate. But perhaps the most awe-inspiring aspect of the Lyman alpha forest is its sheer scale. The forest spans billions of light-years, connecting galaxies across the vast expanse of the universe. It's a reminder of the interconnectedness of everything in the cosmos, from the smallest hydrogen atom to the largest galaxy cluster. And it's a testament to human ingenuity that we've found a way to read this cosmic map, using nothing more than light and the fundamental properties of matter. Despite all we've learned, the Lyman alpha forest still holds many mysteries. For instance, why is the intergalactic medium as smooth as it is? Simulations suggest that small-scale structures should be more pronounced, but observations of the forest show a surprisingly uniform distribution of matter. Could this discrepancy point to new physics, or is it simply a limitation of our models? Similarly, what role does feedback from galaxies and quasars play in shaping the forest? These are questions that future telescopes, like the Extremely Large Telescope and the James Webb Space Telescope, aim to answer. The future of exploring the Lyman alpha forest is incredibly exciting. Advanced telescopes and improved computational models are poised to shed even more light on this intricate cosmic web. These tools will allow astronomers to map the Lyman alpha forest with unprecedented precision, revealing details about the distribution of matter, the behavior of hydrogen in various cosmic environments, and the fundamental forces at play in the universe. One significant step forward involves the use of next-generation observatories. The James Webb Space Telescope, JWST, for instance, is already revolutionizing our ability to observe distant quasars and faint galaxies. Its advanced infrared capabilities enable it to peer through cosmic dust and capture the faint light of objects from the early universe. With JWST, astronomers can identify more quasars at extreme redshifts, offering a more detailed view of the Lyman alpha forest during the era of reionization. Additionally, ground-based telescopes like the Extremely Large Telescope, ELT, will play a crucial role in studying the forest. The ELT, with its enormous 39-meter mirror, will have the sensitivity and resolution needed to analyze the spectra of thousands of quasars. This will allow astronomers to create a three-dimensional map of the Lyman alpha forest, charting the distribution of hydrogen across vast cosmic distances. These observations will be instrumental in refining our understanding of the universe's large-scale structure and the physics driving its evolution. Another exciting development is the synergy between observational data and advanced simulations. Supercomputers are now capable of running simulations that model the formation of the Lyman alpha forest in remarkable detail, incorporating the complex interplay between dark matter, baryonic matter, and radiation. By comparing these simulations with real-world observations, scientists can test and refine their theories about the universe's early stages. For example, one area of interest involves understanding the transition from neutral to ionized hydrogen during reionization. Simulations suggest that this process was not uniform but instead occurred in patches, with regions of ionized hydrogen expanding outward from galaxies and quasars. Observations of the Lyman alpha forest can confirm these predictions and provide insights into the timing and scale of reionization. Moreover, the Lyman alpha forest can be used to study the impact of cosmic inflows and outflows. Galaxies interact with their surroundings through processes like gas accretion, where material from the intergalactic medium falls into the galaxy, fueling star formation, and galactic winds, where energy from stars and black holes pushes gas out into space. These processes leave distinct signatures in the Lyman alpha forest, offering clues about how galaxies grow and evolve over time. One particularly intriguing aspect of the Lyman alpha forest is its potential to probe the properties of dark matter. Dark matter makes up most of the universe's mass, yet its nature remains one of the biggest mysteries in physics. By studying the small-scale structures in the Lyman alpha forest, astronomers can test different models of dark matter. For instance, if dark matter is warm rather than cold, it would suppress the formation of small-scale structures, leading to smoother absorption patterns in the forest. Observations of the Lyman alpha forest have already provided some of the most stringent constraints on the properties of dark matter, ruling out certain theories and narrowing the field of possibilities. The forest also offers a unique window into the effects of cosmic feedback. Feedback mechanisms, such as supernova explosions and quasar outbursts, can inject energy into the intergalactic medium, heating and ionizing the gas. This feedback can alter the distribution of hydrogen and leave imprints in the Lyman alpha forest. By studying these imprints, scientists can learn more about how galaxies regulate their growth and interact with their surroundings. In addition to its scientific value, the Lyman alpha forest has a philosophical significance that's hard to ignore. It serves as a reminder of how interconnected the universe is. The light from a quasar billions of light years away carries with it the history of the hydrogen it passed through, linking us to distant epochs and regions of space. Each absorption line is like a page in a cosmic diary, telling the story of how matter has moved, changed, and evolved over billions of years. And yet, for all its richness, the Lyman alpha forest is just one piece of a much larger puzzle. It's a glimpse into the universe's hidden scaffolding, but it also raises questions about what lies beyond. What other patterns, forces, and phenomena remain undiscovered? How do the pieces of this vast cosmic puzzle fit together to create the universe we see today? The exploration of the Lyman alpha forest is also a testament to human curiosity and ingenuity. It's incredible to think that by analyzing the light of quasars, we can map the distribution of hydrogen across billions of light years. This achievement is a testament to the power of science to uncover hidden truths and expand our understanding of the cosmos. Looking ahead, there's no doubt that the study of the Lyman alpha forest will continue to yield surprising discoveries. As technology advances and our observational capabilities improve, we'll gain new insights into the universe's earliest moments, the behavior of dark matter, and the complex interplay between galaxies and their environments. These discoveries will not only deepen our understanding of the cosmos but also inspire new questions and challenges for future generations of scientists. The Lyman Alpha Forest is more than just a tool for studying the universe. It's a bridge connecting us to the cosmos. It's a reminder that even in the vastness of space, there's a hidden order, a web of connections that binds everything together. And as we continue to explore this hidden map, we're not just learning about the universe. We're also learning about ourselves, our place in the cosmos, and the incredible power of human curiosity. The quest to understand the Lyman Alpha Forest also carries profound implications for cosmology, the study of the universe's origins and evolution. By examining the forest, scientists can test and refine the standard cosmological model, which describes how the universe expanded and formed its current structure after the Big Bang. The Lyman Alpha Forest acts as a powerful probe into the interplay of matter, energy, and fundamental forces on a cosmic scale. One of the most fascinating aspects of this investigation is how the Lyman Alpha Forest provides a direct connection to the universe's expansion. The absorption lines in the forest are stretched, or redshifted, due to the expansion of space itself. This redshift is not only a measure of distance but also a timestamp that tells us when the light passed through the intervening hydrogen clouds. By analyzing these redshifts, scientists can reconstruct a timeline of the universe's history, pinpointing key events like reionization, galaxy formation, and the emergence of large-scale cosmic structures. The ability to measure the redshift of hydrogen absorption lines with such precision also enables astronomers to study the universe's acceleration due to dark energy. Dark energy, the mysterious force driving the accelerated expansion of the universe, has remained one of the most enigmatic components of the cosmos. The Lyman Alpha Forest offers a way to track the rate of expansion over time, providing crucial data that can refine models of dark energy and its role in shaping the universe. Beyond its utility for understanding the universe's expansion, the Lyman Alpha Forest is also a critical tool for testing theories of gravity. General relativity, Einstein's groundbreaking theory, has stood the test of time as the cornerstone of our understanding of gravity. However, some alternative theories suggest modifications to general relativity on large scales, particularly when accounting for dark matter and dark energy. By studying the distribution and dynamics of hydrogen in the Lyman Alpha Forest, scientists can test whether gravity behaves as predicted by general relativity, or if new physics is required. The forest's potential to reveal new physics doesn't stop with gravity. It also provides a window into the behavior of fundamental particles and forces in the early universe. For example, the density and distribution of hydrogen in the Lyman Alpha Forest are influenced by the temperature and ionization state of the intergalactic medium. These, in turn, are shaped by processes like cosmic reionization and the interaction of matter with radiation. By studying these interactions, scientists can test models of particle physics and gain insights into phenomena like the nature of neutrinos or the existence of exotic particles. One of the most intriguing mysteries connected to the Lyman Alpha Forest is the so-called missing baryon problem. Baryons, the particles that make up ordinary matter, were abundant in the early universe, but only a fraction of them are visible today in stars, galaxies, and hot gas. The Lyman Alpha Forest provides a way to trace these missing baryons, as they may reside in diffuse gas that absorbs quasar light. Observations of the forest have already revealed evidence of these elusive baryons, helping to close a critical gap in our understanding of the universe's matter content. The study of the Lyman Alpha Forest has also spurred innovations in data analysis and machine learning. The sheer volume of spectral data generated by modern telescopes requires advanced computational techniques to process and interpret. Machine learning algorithms are now being used to identify subtle patterns in the forest, classify absorption lines, and even predict the properties of intervening hydrogen clouds. These tools are accelerating the pace of discovery and opening new avenues for exploration. Machine learning models trained on large datasets of simulated Lyman Alpha Forest spectra are also helping astronomers refine their theoretical frameworks. By comparing real-world observations to simulated data, scientists can pinpoint discrepancies, test hypotheses, and improve their understanding of how the universe operates on both small and large scales. A particularly captivating application of machine learning in studying the Lyman alpha forest is its ability to detect anomalies, unexpected features that deviate from standard cosmological models. These anomalies could indicate unknown phenomena, such as the influence of exotic particles, variations in fundamental constants, or the presence of structures in the universe that defy conventional understanding. In this way, the forest may not just validate existing theories but also open doors to entirely new realms of physics. Another groundbreaking use of the Lyman alpha forest involves examining the interplay between galaxies and their surrounding environments. While galaxies are often studied in isolation, the reality is that they exist within the larger framework of the cosmic web. The forest serves as a bridge between the intergalactic medium and galaxy formation, revealing how gas flows into and out of galaxies and how these processes influence star formation, supermassive black hole growth, and the chemical evolution of galaxies. For example, astronomers have found that galaxies embedded in dense regions of the cosmic web often exhibit higher rates of star formation. This is likely due to the abundant supply of cold gas funneled along filaments of the web. The Lyman alpha forest captures these gas flows, providing direct evidence of how galaxies feed on the intergalactic medium. Conversely, powerful outflows driven by supernovae or active galactic nuclei can heat and disperse gas, leaving imprints in the forest that reveal how galaxies shape their surroundings. These interactions highlight the dynamic and interconnected nature of the universe. Far from being static, the cosmic web is a living system, constantly evolving and adapting as galaxies grow, merge, and transform. The Lyman alpha forest offers a rare glimpse into this dynamism, showing us not only where matter is but also how it moves, interacts, and changes over time. The forest's role as a cosmic map also extends to the search for the earliest galaxies and quasars. These ancient objects are the building blocks of the universe as we know it, and their light illuminates the hydrogen clouds that make up the forest. By identifying these early beacons, astronomers can probe the conditions that gave rise to the first stars and galaxies, shedding light on how the universe transitioned from a dark, neutral state to the luminous cosmos we see today. This search has led to some of the most profound discoveries in modern astronomy. For instance, observations of the Lyman alpha forest have confirmed that the universe underwent a phase known as cosmic dawn, when the first stars and galaxies began to emit light and reionize the surrounding hydrogen. This epoch, which occurred roughly 500 million years after the Big Bang, marked a pivotal turning point in cosmic history. The forest provides a detailed record of this transition, revealing the timing, scale, and complexity of reionization. Moreover, the forest has helped identify regions of the universe that are unusually empty or dense. These cosmic voids and overdensities offer valuable insights into the universe's large-scale structure and the forces that shape it. Voids, for example, are vast regions with few galaxies or matter, and their properties can test theories of dark energy and modified gravity. Overdensities, on the other hand, are rich in matter and often host massive galaxy clusters. The Lyman alpha forest allows scientists to trace these structures and understand how they form and evolve. One of the most thrilling aspects of studying the Lyman alpha forest is its ability to connect the smallest scales of physics with the largest scales of the cosmos. The patterns in the forest are influenced by quantum processes that occurred during the universe's infancy, such as the inflationary epoch. Inflation is a theorized period of rapid expansion that smoothed and stretched the fabric of spacetime, creating the initial density fluctuations that later grew into galaxies and clusters. By analyzing the forest, scientists can test predictions of inflationary models and gain insights into the universe's earliest moments. This interplay between micro and macro is a testament to the universality of physics. It shows that the same principles governing particles and forces at the smallest scales also shape the largest structures in the universe. The Lyman alpha forest is a bridge between these realms, offering a unified perspective on how the cosmos operates. The implications of these discoveries extend beyond academia. They inspire awe and wonder about the universe's complexity and beauty, reminding us of our place in a vast and interconnected cosmos. They also underscore the importance of collaboration and innovation, as the study of the Lyman alpha forest requires expertise from diverse fields, from astrophysics to computer science. As we look to the future, the Lyman alpha forest will continue to be a cornerstone of cosmic exploration. With upcoming projects like the Square Kilometre Array, SKA, and advancements in computational astrophysics, the forest's potential is boundless. These efforts will bring us closer to unraveling the mysteries of the universe, one absorption line at a time. The journey to unravel the secrets of the Lyman alpha forest is far from over. With technological advancements and the construction of new, highly sensitive telescopes, astronomers are poised to explore the forest in unprecedented detail. For example, the upcoming Extremely Large Telescope, ELT, and James Webb Space Telescope, JWST, promise to revolutionize our understanding of the distant universe. These instruments will allow scientists to detect fainter quasars and analyze their spectra with higher precision, thereby extending our view deeper into cosmic history. One of the most exciting prospects for these telescopes is their ability to observe the faint remnants of the first stars and galaxies. These primordial objects, formed just a few 100 million years after the Big Bang, are thought to have played a key role in shaping the intergalactic medium. Their intense ultraviolet radiation ionized the surrounding hydrogen, creating bubbles of ionized gas that gradually expanded and merged during the epoch of reionization. By studying the Lyman alpha forest in the light of these early sources, scientists can piece together a detailed timeline of how reionization unfolded and how the first structures in the universe came to be. The JWST, in particular, is expected to be a game-changer for this field. Its infrared capabilities make it uniquely suited for detecting light from the most distant quasars and galaxies, whose emissions have been stretched to longer wavelengths by the universe's expansion. By examining the Lyman alpha forest in these sources, astronomers can probe the conditions of the intergalactic medium at an earlier stage than ever before. This could provide critical insights into the formation of the first black holes, the emergence of chemical elements, and the processes that seeded the universe with the building blocks of life. Another frontier in the study of the Lyman alpha forest involves its use as a tool for precision cosmology. Over the past 2 decades, scientists have made remarkable progress in mapping the large-scale structure of the universe using surveys of galaxies and the cosmic microwave background, CMB. However, the Lyman alpha forest offers a complementary perspective, as it traces the distribution of matter on smaller scales and at higher redshifts. By combining data from galaxy surveys, the CMB, and the forest, scientists can create a more complete and accurate picture of the universe's structure and evolution. This synergy is particularly important for studying dark energy, the mysterious force driving the accelerated expansion of the universe. While galaxy surveys have provided valuable constraints on the properties of dark energy, they are limited to relatively low redshifts, corresponding to the recent past. The Lyman alpha forest, by contrast, extends our view to much higher redshifts, offering a glimpse of the universe when it was younger and denser. By measuring the clustering of hydrogen absorption lines in the forest, scientists can infer the distribution of dark energy over cosmic time and test whether its properties have changed. The forest also has the potential to shed light on another enduring mystery: the nature of dark matter. Unlike dark energy, dark matter does not cause the universe to expand. Instead, it exerts a gravitational pull that helps hold galaxies and clusters together. The Lyman alpha forest provides a unique way to study dark matter, as the distribution of hydrogen in the intergalactic medium is shaped by the gravitational influence of dark matter halos. By analyzing the small-scale structure of the forest, scientists can test different models of dark matter and constrain its properties, such as its mass and interaction strength. Intriguingly, the forest may also reveal clues about alternative theories of gravity. Some physicists have proposed modifications to general relativity to explain the behavior of dark matter and dark energy without invoking new particles. These theories predict subtle differences in the clustering of matter that could be detectable in the Lyman alpha forest. By comparing observations of the forest with predictions from these models, scientists can test the validity of Einstein's theory on cosmic scales and search for signs of new physics. The potential discoveries don't stop there. The Lyman alpha forest is also a promising tool for studying the influence of neutrinos, the elusive particles that are among the most abundant in the universe but interact very weakly with matter. Neutrinos have a small mass, which affects the formation of cosmic structures by suppressing the growth of small-scale fluctuations. This effect leaves a distinctive imprint on the Lyman alpha forest, allowing scientists to measure the sum of neutrino masses and test theories of particle physics. Beyond its implications for cosmology and fundamental physics, the Lyman alpha forest also has practical applications for understanding the environment of our own galaxy. The intergalactic medium is not isolated from the Milky Way. Instead, there is a constant exchange of gas between galaxies and their surroundings. This exchange plays a crucial role in regulating star formation, chemical enrichment, and the growth of supermassive black holes. By studying the forest, scientists can trace the flow of gas into and out of galaxies and learn how these processes shape the evolution of the Milky Way. One of the most fascinating aspects of this research is its potential to reveal the universe's hidden connections. The cosmic web, with its intricate network of filaments, nodes, and voids, is not just a random arrangement of matter but a reflection of the universe's underlying laws. The patterns in the Lyman alpha forest are shaped by these laws, from the quantum fluctuations that seeded the web to the gravitational forces that shaped it. By decoding the forest, we are uncovering the cosmic blueprint that governs the universe's structure and behavior. The journey to understand the Lyman alpha forest is a testament to human curiosity and ingenuity. It has required the development of cutting-edge telescopes, the creation of sophisticated simulations, and the collaboration of scientists from around the world. Each discovery has raised new questions, spurring further exploration and innovation. And while we have made remarkable progress, the forest continues to hold secrets that challenge our understanding and inspire our imagination. As we look to the future, one thing is clear: the Lyman alpha forest will remain a vital tool for exploring the cosmos. Whether we are studying the origins of the first galaxies, the nature of dark matter and dark energy, or the fundamental laws of physics, the forest provides a window into the universe's most profound mysteries. It reminds us that the cosmos is a vast and interconnected system, full of wonders waiting to be discovered. The light of distant quasars, traveling across billions of years and countless hydrogen clouds, carries a story of the universe's evolution. Through the Lyman alpha forest, we are learning to read that story, line by line, uncovering the secrets of the cosmos and our place within it. It is a journey of discovery that will continue for generations to come, driven by our unending desire to understand the universe and its hidden truths. The exploration of the Lyman alpha forest is not only a journey into the distant past but also an investigation into the physical processes that shape the universe we observe today. The absorption lines in the spectra of quasars are like fingerprints, each one telling a unique story about the density, temperature, and composition of the intergalactic medium, IgM, it passed through. By carefully analyzing these fingerprints, astronomers can reconstruct a three-dimensional map of the cosmic web. This mapping process is akin to solving an intricate puzzle. The quasars act as backlights, illuminating the intervening hydrogen clouds and revealing their structures. Each quasar provides a one-dimensional slice of the universe along the line of sight. By combining observations from multiple quasars, scientists can piece together a more complete picture of the IgM. This technique, known as tomography, is revolutionizing our understanding of the large-scale structure of the universe. One of the most striking discoveries made through Lyman alpha forest tomography is the detailed visualization of the cosmic web. Computer simulations based on the principles of cosmology and astrophysics predict that matter in the universe is distributed in a vast network of filaments and voids. The filaments are regions of relatively high density, where galaxies and galaxy clusters form, while the voids are vast expanses of low-density gas. The Lyman alpha forest provides observational evidence of this structure, confirming the accuracy of these simulations and offering new insights into the processes that shape the web. A particularly fascinating aspect of the Lyman alpha forest is its ability to reveal the influence of feedback mechanisms on the IgM. Feedback refers to the effects of energy and matter ejected by galaxies and black holes on their surroundings. For example, supernova explosions and winds from massive stars can blow gas out of galaxies, enriching the IgM with heavy elements. Similarly, the intense radiation and powerful jets produced by supermassive black holes can heat and ionize the surrounding gas, creating complex structures in the cosmic web. These feedback processes are imprinted on the Lyman alpha forest as variations in the strength and shape of the absorption lines. By studying these variations, scientists can learn about the life cycles of galaxies and the interplay between matter and energy in the universe. For instance, the forest reveals how galaxies acquire the gas needed to form stars and how this gas is recycled back into the IgM. It also sheds light on the impact of black hole activity on galaxy evolution, helping to answer questions about the coevolution of galaxies and their central black holes. Another intriguing application of the Lyman alpha forest is its use as a probe of the thermal history of the universe. The IgM's temperature is determined by a delicate balance between heating and cooling processes. Heating occurs primarily through the ionization of hydrogen and helium by ultraviolet radiation from stars and quasars, while cooling is driven by the emission of radiation from the gas itself. The forest provides a record of this thermal history, with the widths of the absorption lines serving as a thermometer for the IgM. One key period in the thermal history of the universe is the epoch of helium reionization. While hydrogen reionization occurred relatively early, during the first billion years after the Big Bang, helium reionization took place several billion years later, when quasars became more numerous and energetic. This second wave of reionization had a profound impact on the IgM, heating the gas to temperatures of tens of thousands of degrees. The Lyman alpha forest provides a unique window into this era, allowing scientists to study the timing and effects of helium reionization in detail. The forest also offers a glimpse into the physical properties of the first galaxies and stars. These early sources of light, known as population 3 stars, are thought to have been massive, short-lived, and extremely bright. Their radiation ionized the surrounding hydrogen, creating bubbles of ionized gas that expanded and merged over time. These bubbles left an imprint on the Lyman alpha forest, providing indirect evidence of the first stages of galaxy formation. By analyzing these imprints, astronomers can learn about the properties of population 3 stars and their role in shaping the IgM. As we delve deeper into the mysteries of the Lyman alpha forest, we are also pushing the limits of technology and innovation. The development of new instruments and techniques is enabling more precise and comprehensive observations of the forest. For example, next-generation spectrographs, such as those planned for the ELT and other large telescopes, will provide higher-resolution data, revealing finer details of the absorption lines. This will allow scientists to study smaller-scale structures in the IgM and test theoretical models with greater accuracy. In addition to ground-based telescopes, space-based observatories are playing a crucial role in advancing our understanding of the Lyman alpha forest. The Hubble Space Telescope, for instance, has been instrumental in observing the forest at lower redshifts, where the ultraviolet light of quasars can still be detected. Future missions, such as the JWST and the proposed LUVOIR, Large UV/Optical/IR Surveyor, promise to extend these observations to even higher redshifts and fainter sources, opening new windows into the early universe. The study of the Lyman alpha forest is a collaborative effort that spans. It involves astronomers, physicists, computer scientists, and statisticians, all working together to decode the information encoded in the forest. It also relies on massive datasets and sophisticated algorithms to analyze the spectra of thousands of quasars and identify patterns in the absorption lines. This interdisciplinary approach is driving progress in both science and technology, with applications that extend beyond astronomy. For example, the techniques developed for analyzing the Lyman alpha forest are being used to study other astrophysical phenomena, such as the distribution of gas and dust in the Milky Way and the properties of exoplanet atmospheres. They are also inspiring advances in machine learning and data science, with algorithms originally designed for forest analysis being applied to problems in fields ranging from biology to finance. Ultimately, the Lyman alpha forest is a reminder of the power of curiosity and the importance of looking beyond the surface. What began as a puzzling pattern of lines in the spectra of distant quasars has become one of the most valuable tools for exploring the universe. It has revealed the structure of the cosmic web, the thermal history of the IGM, and the processes that shape galaxies and black holes. It has challenged our understanding of dark matter, dark energy, and fundamental physics. And it has shown us that even the faintest traces of light can illuminate the darkest corners of the cosmos. As we continue to study the Lyman Alpha Forest, we are not only uncovering the secrets of the universe but also pushing the boundaries of human knowledge and imagination. The forest is a testament to the complexity and beauty of the cosmos, a hidden map that guides us on our journey to understand the origins and destiny of everything we see. And while we have come a long way, there is still so much more to discover, ensuring that the forest will remain a source of wonder and inspiration for generations to come. The Lyman Alpha Forest continues to inspire groundbreaking research, with each discovery deepening our appreciation for the intricate tapestry of the universe. At its core, the forest reveals how the simplest element, hydrogen, can serve as the universe's most profound storyteller. Every absorption line etched into a quasar's light carries encoded information about the cosmic conditions it encountered during its journey, much like how tree rings document the environmental history of a forest. Beyond mapping the cosmic web and tracing the thermal history of the intergalactic medium, the Lyman Alpha Forest is central to exploring the elusive mysteries of dark matter and dark energy. These two phenomena, though invisible, exert a profound influence on the universe's structure and evolution. Dark matter, responsible for the gravitational scaffolding of the cosmic web, shapes the density and distribution of hydrogen gas observed in the forest. Meanwhile, dark energy, driving the accelerated expansion of the universe, leaves subtle yet measurable imprints on the large-scale distribution of these absorption lines. By comparing observations of the Lyman Alpha Forest with simulations of cosmic evolution, astronomers refine their models of dark matter's properties. The forest's delicate patterns help constrain the mass of hypothetical dark matter particles and shed light on whether dark matter behaves as a cold, warm, or hot component of the universe. These insights guide researchers as they work to unify the physics of the very large, the cosmos, and the very small, subatomic particles. The Lyman Alpha Forest also provides a unique vantage point for testing the fundamental constants of nature. These constants, such as the fine structure constant and the proton-to-electron mass ratio, are thought to be immutable. However, some theories suggest that these constants may have varied slightly over cosmic time. By studying the precise wavelengths of absorption lines in the forest, researchers can test this idea. Any variations in these constants could challenge our understanding of the laws of physics and open new avenues for theoretical exploration. Another captivating aspect of the Lyman Alpha Forest is its role in cosmological chronometry, the measurement of time across the universe's history. The forest serves as a clock that chronicles the universe's growth, tracing the progression of hydrogen's ionization states, temperatures, and densities over billions of years. By aligning these ticks with other cosmic events, such as the formation of the first galaxies or the emergence of large-scale structure, astronomers create a coherent timeline of the universe's evolution. Even the gaps in the forest, regions where absorption lines are weaker or absent, tell their own stories. These gaps correspond to voids in the cosmic web, where the intergalactic medium is sparse and undisturbed. Such regions are crucial for understanding how gravitational forces shape matter on the largest scales and provide a contrast to the denser, more turbulent environments of filaments and clusters. Studying these voids enriches our knowledge of the universe's diversity and underscores the importance of empty space in the cosmic balance. One of the most exciting developments in the study of the Lyman Alpha Forest is the advent of advanced computational simulations. These simulations, powered by supercomputers, replicate the universe's evolution from its earliest moments to the present day. By comparing the simulated absorption lines with those observed in quasar spectra, scientists can test the accuracy of their models and refine their understanding of the processes that govern cosmic history. These simulations are not mere theoretical exercises. They are essential tools for interpreting the Lyman Alpha Forest. They allow researchers to disentangle the effects of various physical phenomena, such as gravitational collapse, radiation heating, and gas dynamics, which are intricately intertwined in the forest. They also enable astronomers to predict how the forest might appear under different cosmological scenarios, providing a framework for testing alternative theories of the universe's origins and fate. The future of Lyman alpha forest research looks incredibly promising, thanks to upcoming technological advancements. The next generation of telescopes, including the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will offer unprecedented sensitivity and resolution. These instruments will allow astronomers to observe fainter and more distant quasars, extending the reach of the Lyman alpha forest into the earliest epochs of the universe. In addition to new telescopes, advances in spectroscopy are revolutionizing the study of the Lyman alpha forest. High-resolution spectrographs, capable of capturing the finest details of quasar spectra, are enabling more precise measurements of absorption lines. These instruments are essential for distinguishing between subtle features in the forest, such as the effects of small-scale turbulence, or the signatures of rare heavy elements. Space-based observatories will also play a pivotal role in the future of Lyman alpha forest research. While ground-based telescopes are limited by Earth's atmosphere, space telescopes can observe the ultraviolet light from quasars without interference. Missions like the proposed LUVOIR, Large UV/Optical/IR Surveyor, aim to study the forest with unparalleled clarity, unlocking new levels of detail and revealing previously unseen aspects of the cosmic web. As our observational capabilities expand, so too does the potential for unexpected discoveries. The Lyman alpha forest, though well-studied, continues to surprise astronomers with its complexity and richness. Each new observation raises fresh questions, challenging our assumptions and driving innovation. Whether through the detection of previously unknown absorption features, the discovery of exotic physical phenomena, or the development of novel analytical techniques, the forest remains a dynamic and evolving field of study. Ultimately, the Lyman alpha forest is a testament to the power of light to reveal the hidden universe. Through its intricate interplay of absorption and emission, the forest uncovers the invisible scaffolding of the cosmos, illuminates the processes that govern its evolution, and provides a bridge between the known and the unknown. It reminds us that even the faintest whispers of light carry profound truths, waiting to be heard by those who dare to listen. As we journey deeper into the forest, we find ourselves not only uncovering the secrets of the cosmos but also gaining a greater appreciation for the unity of nature. From the smallest particles to the grandest galaxies, the universe is a single, interconnected system, where every element plays a role in the cosmic symphony. The Lyman alpha forest is both a map and a melody, guiding us through the darkness and revealing the beauty that lies beyond. The Lyman alpha forest is far from being merely an astronomical curiosity. It is an essential tool for unraveling the most profound questions about the cosmos. By studying this forest of absorption lines, scientists are essentially conducting a cosmic archaeology, uncovering the layers of the universe's past and piecing together its long and complex story. As we delve further, the forest not only allows us to explore the universe's history but also poses new questions about its present and future. One area of active research involves the interaction between galaxies and the intergalactic medium. The Lyman alpha forest provides a window into how galaxies influence their surroundings. For example, galaxies emit ultraviolet radiation that ionizes the hydrogen gas around them. This ionized region, known as the galaxy's proximity zone, is visible in the Lyman alpha forest as a distinct gap in the absorption lines. By studying these zones, astronomers can learn about the energy output of galaxies, the properties of their stars, and even the activity of their central black holes. These proximity zones also help scientists measure the duration and intensity of cosmic reionization. During this epoch, the first stars and galaxies emitted enough energy to ionize the neutral hydrogen that filled the universe after the cosmic dark ages. The patterns in the Lyman alpha forest reveal when this reionization process occurred and how it shaped the universe we observe today. This provides key insights into one of the most transformative periods in cosmic history. In addition, the forest offers a unique method for mapping galactic winds, streams of charged particles ejected from galaxies by supernova explosions or active galactic nuclei. These winds interact with the intergalactic medium, creating ripples that can be detected in the absorption patterns of the forest. By tracking these ripples, astronomers gain insights into the processes that regulate galaxy growth and star formation. This helps us understand why galaxies form in such a wide variety of shapes and sizes, from sprawling spirals to compact ellipticals. The Lyman Alpha Forest also serves as a laboratory for studying the chemistry of the early universe. While hydrogen is by far the most abundant element observed in the forest, tiny amounts of heavier elements, such as carbon, oxygen, and silicon, are also detectable. These elements, known as metals in astronomical terms, were created in the cores of the first stars and dispersed into the intergalactic medium through supernova explosions. By analyzing their distribution and abundance, scientists can trace the cycle of star formation, evolution, and destruction across cosmic time. Even more intriguingly, the forest has the potential to reveal new physics. For example, certain anomalies in the absorption patterns might hint at interactions between dark matter and normal matter that are not predicted by standard theories. Such discoveries could revolutionize our understanding of the universe's composition and the forces that govern it. The Lyman Alpha Forest has also become a key player in the search for the elusive neutrino mass. Neutrinos are subatomic particles that interact very weakly with matter, making them incredibly difficult to study. However, their tiny mass affects the growth of large-scale structures in the universe, leaving subtle imprints in the Lyman Alpha Forest. By analyzing these imprints, astronomers can place limits on the neutrino mass and test theories of particle physics. Another groundbreaking application of the forest is its use in studying the cosmic expansion rate. The universe's expansion has been accelerating due to dark energy, but the details of this acceleration remain poorly understood. The Lyman Alpha Forest provides a way to measure the Hubble parameter, a key indicator of the expansion rate, at different points in cosmic history. This helps refine our understanding of dark energy and its role in shaping the cosmos. Furthermore, the forest is becoming increasingly important in the era of large-scale astronomical surveys. Projects like DESI, Dark Energy Spectroscopic Instrument, and the Vera Rubin Observatory aim to map the three-dimensional structure of the universe with unprecedented precision. The Lyman Alpha Forest is a cornerstone of these efforts, offering a way to chart the distribution of matter across billions of light-years. This complements other techniques, such as galaxy redshift surveys, and creates a more complete picture of the universe's architecture. These surveys are also expected to uncover thousands of new quasars, greatly expanding the dataset available for Lyman Alpha Forest studies. Each new quasar adds another line of sight through the intergalactic medium, providing a more detailed and comprehensive map of the cosmic web. This allows astronomers to study the forest with greater statistical precision and uncover subtle patterns that were previously hidden. As we continue to push the boundaries of what the Lyman Alpha Forest can reveal, it becomes clear that this phenomenon is not just a window into the universe's past but also a bridge to its future. The forest connects us to the earliest epochs of cosmic history, illuminates the present structure of the universe, and guides us toward the answers to some of the most profound questions in science. It is a reminder that even the faintest traces of light can illuminate the darkest corners of the cosmos. The more we learn about the Lyman Alpha Forest, the more we realize how interconnected the universe truly is. Every quasar, every absorption line, and every hydrogen atom is part of a vast and intricate web that binds the cosmos together. By studying this web, we are not only uncovering the secrets of the universe but also gaining a deeper understanding of our place within it. The Lyman Alpha Forest offers a unique glimpse into the larger cosmic structure, but it also has the potential to reveal even more. As new technologies and more powerful telescopes are developed, the ability to observe these distant quasars and their surrounding hydrogen clouds will improve exponentially. The high-resolution spectrographs of the future will enable us to resolve even finer details in the absorption lines, allowing scientists to map the universe with greater accuracy and precision. One of the most exciting future developments in Lyman Alpha Forest studies is the use of next-generation space telescopes. Instruments like the James Webb Space Telescope, JWST, are set to revolutionize our understanding of the early universe. The JWST's infrared capabilities will allow it to study quasars and galaxies in unprecedented detail, pushing the limits of what we can see in the distant past. With its ability to capture the faint light from the first galaxies and quasars, the JWST promises to shed new light on the structure and evolution of the universe, providing even more data on the Lyman alpha forest. This could allow astronomers to trace the earliest stages of cosmic reionization with greater clarity. By observing absorption lines in the Lyman alpha forest from quasars that are even farther away than those currently accessible, we may gain new insights into how and when the universe transitioned from the cosmic dark ages to the more structured, luminous universe we see today. Another frontier for future research lies in the quest to understand the nature of dark matter and dark energy. As we push the boundaries of our knowledge, anomalies in the Lyman alpha forest could provide clues to new physics beyond the standard model. The subtle variations in the absorption lines could be a sign of interactions between dark matter and normal matter, potentially unveiling new particles or forces that have eluded detection so far. The study of the Lyman alpha forest could also lead to advancements in our understanding of the large-scale structure of the universe. The distribution of gas clouds seen in the forest is closely tied to the cosmic web, vast structures of galaxies and dark matter that stretch across the universe. By studying these gas clouds, we can learn more about how galaxies formed and evolved, as well as how they continue to interact with one another. The gravitational pull of these galaxies and clusters of galaxies distorts the light that travels through them, creating a phenomenon known as gravitational lensing. This can provide further insights into the distribution of matter, both visible and invisible, across the universe. As we look toward the future of Lyman alpha forest research, it's important to remember that this is a field still in its infancy. We have only just begun to understand the full potential of these absorption lines as tools for exploring the cosmos. Each discovery opens up new questions and reveals new mysteries, and as technology improves, we'll continue to peel back the layers of the universe's vast history. The Lyman alpha forest is a testament to the power of indirect observation. It shows us that even the faintest traces of light can provide crucial clues about the structure and evolution of the universe. Every quasar, every absorption line, and every hydrogen atom in the forest is a piece of the cosmic puzzle, helping us build a more complete picture of the universe and our place within it. One of the most exciting aspects of the Lyman alpha forest is its ability to teach us about the very fabric of the universe itself. The gas clouds that give rise to the absorption lines are not isolated. They are part of a larger interconnected structure. Understanding how these clouds form and evolve helps us understand the larger forces at play in the universe, forces that govern the behavior of galaxies, stars, and even the dark matter that shapes the cosmic web. As we continue to gather data from ever more distant quasars, we'll be able to trace the evolution of the universe across cosmic time. We'll learn more about the conditions that led to the formation of galaxies and stars, the process of cosmic reionization, and the role that hydrogen gas plays in the ongoing evolution of the universe. The study of the Lyman alpha forest will continue to yield insights into some of the most fundamental questions in astronomy, and as we unlock these secrets, we'll gain a deeper understanding of the universe and our place within it. The quest for knowledge is never truly finished. Every discovery in science opens the door to new questions, and the Lyman alpha forest is no exception. As we continue to study these faint absorption lines, we'll uncover even more mysteries about the cosmos, and with each revelation, we'll come closer to understanding the vast and interconnected web that is the universe. In a way, the Lyman alpha forest serves as a cosmic map, revealing the hidden structures of the universe that are invisible to the naked eye. It is a reminder that the universe is far more complex and mysterious than we can imagine, and that every bit of knowledge we gain opens up new avenues for exploration. Whether we are studying distant quasars, tracing the evolution of galaxies, or searching for new physics, the Lyman alpha forest offers a powerful tool for unlocking the secrets of the cosmos. As our understanding of this incredible phenomenon deepens, we will continue to push the boundaries of what is possible, and the Lyman alpha forest will remain a key player in the search for answers to some of the most profound questions in science. The forest's light, though faint and distant, is a beacon that guides us through the darkness of the unknown, illuminating the path toward a deeper understanding of the universe. The Lyman alpha forest offers not just a view into the past, but a glimpse into the future of astronomical exploration. As our technology continues to advance, so does our ability to observe the universe in finer detail. The more we learn about the hydrogen absorption lines that create the Lyman alpha forest, the better we can map the universe's history and understand its future trajectory. By studying these lines and the hydrogen clouds that form them, we may unlock clues about the nature of cosmic events like the Big Bang, the formation of galaxies, and the mysterious components of the universe, like dark matter and dark energy. The expansion of the universe, which has been accelerating since the Big Bang, leaves a cosmic footprint that can be observed in the form of the Lyman alpha forest. As the universe expands, the light from distant quasars and galaxies is stretched, creating a redshift that makes these absorption lines detectable. In this way, the forest not only serves as a tool for mapping the universe's past but also provides a snapshot of its ongoing evolution. The way these absorption lines change over time, and the patterns they form, could tell us much about the future of the cosmos. For example, they may provide insights into whether the expansion of the universe will continue indefinitely or if some other force, such as dark energy, will eventually cause it to reverse course. What makes the Lyman alpha forest particularly intriguing is the fact that it reveals structures in the universe that are invisible through traditional means. The gas clouds responsible for the absorption lines are often located between galaxies, sometimes in regions that are far removed from the visible structures we typically study. These clouds may seem invisible at first glance, but by observing their effect on the light from distant quasars, we can uncover a hidden layer of cosmic structure. This layer holds the key to understanding how the universe evolved, how galaxies formed, and how the intergalactic medium behaves over time. By using the Lyman alpha forest as a tool for studying the large-scale structure of the universe, we can also learn more about the role that gas plays in the formation and evolution of galaxies. The intergalactic gas clouds that create the absorption lines are not just passive entities in space. They are active participants in the cosmic drama. As they interact with galaxies, these clouds can influence the growth and development of galaxies, affecting star formation and even helping to regulate the flow of gas and energy within these systems. Understanding how this interaction works could help us answer fundamental questions about galaxy formation and evolution. Moreover, studying the Lyman alpha forest could also have implications for the search for extraterrestrial life. The absorption lines in the forest are not just markers of intergalactic gas, they are also markers of the conditions that exist in the spaces between galaxies. These conditions, including temperature, density, and composition, could have a direct impact on the potential for life to exist in other parts of the universe. If we are to ever find life beyond Earth, understanding the environments in which it might thrive could be key, and the Lyman alpha forest may offer a crucial piece of that puzzle. The hunt for new phenomena within the Lyman alpha forest is not just about studying what is already known, it's about discovering the unknown. As astronomers continue to study the absorption lines created by these distant hydrogen clouds, they are uncovering new and surprising features. For example, in some cases, scientists have observed the presence of heavy elements, such as metals, that are not typically found in such regions of space. These metals may be the remnants of supernova explosions, providing evidence for the process of galactic evolution. The presence of such heavy elements could change the way we think about the formation of galaxies and the role of intergalactic gas. In addition, the study of the Lyman alpha forest is helping astronomers refine their models of cosmic reionization. Reionization is the process by which the universe transitioned from being opaque to transparent, allowing light to travel freely through space. This transition occurred when the first stars and galaxies formed and began emitting ultraviolet radiation, which ionized the hydrogen gas in the universe. The Lyman alpha forest serves as a critical tool for studying this process, as the absorption lines in the forest are a direct consequence of the ionization of hydrogen. By studying the properties of these lines, scientists can learn more about the timing and nature of reionization, as well as how it affected the evolution of the universe. The Lyman alpha forest is also a powerful tool for understanding the distribution of matter in the universe. The hydrogen gas responsible for the absorption lines is not uniformly distributed. Instead, it is found in clumps and filaments that are woven throughout the vast expanse of space. These clumps of gas are often linked to the large-scale structure of the universe, such as the cosmic web of galaxies and dark matter. By studying the Lyman alpha forest, astronomers can map these clumps and filaments, revealing the intricate network of matter that shapes the universe's structure. As we continue to study the Lyman alpha forest, we may also begin to uncover new insights into the nature of the intergalactic medium itself. The intergalactic medium, the gas that exists between galaxies, is an area of active research, and the Lyman alpha forest provides a unique way to probe this mysterious region of space. By studying how light is absorbed by hydrogen gas in the intergalactic medium, astronomers can learn more about the physical properties of this gas, such as its temperature, density, and composition. This could help us understand how the intergalactic medium affects the growth of galaxies, the distribution of dark matter, and the overall evolution of the universe. In many ways, the Lyman alpha forest is like a cosmic detective story. The light from distant quasars acts as a messenger, revealing hidden details about the universe that would otherwise remain out of reach. As astronomers continue to unravel the mysteries encoded in these absorption lines, they are piecing together a more complete picture of the cosmos. What was once a faint and mysterious phenomenon is now one of the most powerful tools in the astronomer's arsenal, helping us map the universe, trace its history, and predict its future. Looking ahead, the study of the Lyman alpha forest will only continue to grow in importance. With new observatories and increasingly sophisticated technologies on the horizon, we are poised to uncover even more secrets hidden within this cosmic map. From understanding the formation of galaxies to unraveling the mysteries of dark matter and dark energy, the Lyman alpha forest holds the potential to transform our understanding of the universe. The Lyman alpha forest is much more than just a collection of absorption lines in the spectrum of distant quasars. It is a gateway to understanding the universe's history, structure, and future. As we continue to study it, we will uncover more about the nature of cosmic evolution, the behavior of hydrogen gas, and the hidden forces that shape the cosmos. The Lyman alpha forest is a powerful reminder that the universe is full of mysteries waiting to be uncovered, and that even the faintest traces of light can reveal profound truths about the nature of reality. The exploration of the Lyman alpha forest is not only a journey into understanding the universe's past but also an opportunity to probe its deepest secrets. With every advancement in technology and every new discovery, we are pushing the boundaries of what we know about the cosmos. And the Lyman alpha forest, in its intricate web of hydrogen absorption lines, provides a rich and complex tapestry from which to unravel these mysteries. One of the key breakthroughs in understanding the Lyman alpha forest is the development of new spectroscopic techniques that allow astronomers to analyze these absorption lines with unprecedented precision. Instruments like the Hubble Space Telescope and the Keck Observatory have already provided stunning insights into the structure of the forest. However, as the next generation of telescopes, such as the James Webb Space Telescope, JWST, come online, the data we collect will only become more detailed. This new wealth of information will open up entirely new avenues of inquiry. The JWST, with its advanced infrared capabilities, will be able to detect even more distant quasars and galaxies, extending the reach of the Lyman alpha forest back in time to when the universe was in its infancy. This could potentially allow us to observe the earliest stages of galaxy formation and cosmic evolution, shedding light on events that took place over 13 billion years ago. Additionally, as more powerful computational models are developed, the analysis of the Lyman alpha forest will become more sophisticated. These models, which simulate the interactions between light and hydrogen gas, are key to understanding the processes that give rise to the forest's distinctive absorption lines. As our simulations improve, we'll be able to not only map the distribution of hydrogen in the universe but also better understand the physical properties of the intergalactic medium. For instance, current models suggest that the temperature of the intergalactic medium is likely to vary over time, and by studying how the absorption lines evolve in response to these changes, we can gain valuable insights into the cooling and heating processes that govern the intergalactic gas. Beyond providing a window into the early universe, the Lyman alpha forest also plays a crucial role in helping us understand the distribution of dark matter. Dark matter, the mysterious substance that makes up approximately 85% of the universe's mass, cannot be directly observed, but its presence is inferred by its gravitational effects on visible matter. By studying the way the absorption lines in the Lyman alpha forest are affected by the gravitational pull of unseen dark matter, astronomers can gain new insights into its distribution and behavior. This is particularly exciting because understanding dark matter is one of the most pressing challenges in modern astrophysics. The Lyman alpha forest may not just be a tool for mapping hydrogen, but a key to uncovering the invisible structures that shape the universe. Moreover, the Lyman alpha forest is helping to answer one of the most fundamental questions in cosmology: how galaxies form and evolve. By studying the gas that surrounds galaxies, astronomers can better understand how galaxies acquire the gas they need to fuel star formation and how this gas interacts with the galaxies themselves. In many ways, the Lyman alpha forest acts as a bridge between the galaxies and the vast regions of space between them, providing critical information about the processes that drive galactic evolution. It is in these regions of intergalactic space, where hydrogen gas exists in vast, often invisible clouds, that the conditions for galaxy formation and evolution are set into motion. The way the Lyman alpha forest reveals this cosmic story is nothing short of fascinating. As the light from quasars passes through these intergalactic clouds of hydrogen, the resulting absorption lines in the quasar's spectrum tell us not just about the gas itself but about the environment in which it exists. The lines can tell us about the temperature and density of the hydrogen gas, the distance of the cloud from the quasar, and even the velocity at which the gas is moving. These details allow astronomers to reconstruct the physical conditions in the universe at different points in time, giving us a clearer picture of how the universe evolved and how galaxies formed from the primordial gas that existed in the early universe. In recent years, astronomers have also begun to explore the role of the Lyman alpha forest in the study of supermassive black holes, which are found at the centers of most galaxies. These black holes are thought to play a critical role in the formation and evolution of galaxies, yet their exact role in this process is still a mystery. By studying the way absorption lines in the Lyman alpha forest are affected by the gravitational and electromagnetic influence of black holes, scientists hope to uncover new insights into the interplay between these enigmatic objects and the galaxies they inhabit. As our understanding of black holes deepens, the Lyman alpha forest may prove to be a key tool in unraveling the mysteries of these cosmic giants. The Lyman alpha forest also provides important clues about the behavior of the early universe, especially in relation to the process of cosmic reionization. This period, which occurred about 13 billion years ago, marked the transition from a dark, opaque universe to one filled with the light of the first stars and galaxies. During this time, ultraviolet radiation from the first stars ionized the hydrogen gas that filled the universe, allowing light to travel freely and shaping the structure of the cosmos. The absorption lines in the Lyman alpha forest are a direct consequence of this ionization, and by studying these lines, scientists can gain a better understanding of when and how reionization occurred. Understanding this process is critical for several reasons, including its implications for the formation of galaxies and the emergence of large-scale structures in the universe. In addition to their role in studying the early universe, the absorption lines in the Lyman alpha forest also offer insights into the current state of the universe. By analyzing the density and distribution of hydrogen gas in the intergalactic medium, astronomers can learn more about the overall structure of the universe and how it continues to evolve. For example, studying how the absorption lines are distributed across different regions of the sky can reveal the presence of large-scale structures like galaxy clusters and cosmic voids. These structures, which form the cosmic web, are a fundamental feature of the universe, and understanding their distribution is key to understanding the forces that shape the cosmos. Another area where the Lyman alpha forest is proving to be invaluable is in the study of cosmic inflation, the rapid expansion of the universe that occurred in the first moments after the Big Bang. This period of inflation is thought to have played a crucial role in shaping the structure of the universe as we see it today. By examining the way the Lyman alpha forest reveals the distribution of hydrogen gas at different distances from Earth, astronomers can gain insights into how inflation affected the evolution of the cosmos. This could ultimately lead to a deeper understanding of the very origins of the universe itself. The study of the Lyman alpha forest is also becoming increasingly important in the search for habitable exoplanets. As astronomers discover more and more planets outside our solar system, the search for potentially habitable worlds has become one of the most exciting areas of research. One of the key factors in determining whether a planet can support life is its atmosphere. The Lyman alpha forest may help us in this search by providing clues about the atmospheres of exoplanets. By studying the absorption lines in the light from distant stars and quasars, astronomers can learn about the chemical composition of the atmospheres of planets that are billions of light years away. This could help us identify planets that have the potential to support life, and in turn, guide future missions to explore these distant worlds. In the grand scheme of cosmic exploration, the Lyman alpha forest is one of the most powerful tools we have at our disposal. It allows us to map the vast, unseen regions of space and to peer into the deepest corners of the universe's past. As we continue to refine our techniques and develop more sophisticated instruments, the Lyman alpha forest will only grow in importance. It holds the potential to unlock many of the universe's greatest mysteries, from the nature of dark matter and dark energy to the origins of galaxies, stars, and planets. And in the process, it may help us answer the most profound question of all: what is the nature of the universe we call home? The Lyman alpha forest serves as a cosmic canvas, painted with the absorption lines of hydrogen gas stretching across the vastness of the universe. Every observation we make through advanced telescopes like the James Webb Space Telescope and the Hubble Space Telescope brings us closer to understanding the intricate relationship between matter and light, and how the universe itself continues to evolve. But as our tools become more powerful and our understanding deepens, we are faced with even more questions about the role these absorption lines play in the bigger picture of cosmic history. A particularly compelling question that arises from the study of the Lyman alpha forest is how these absorption features can help us trace the timeline of the universe's expansion. The universe, as we know, has been expanding ever since the Big Bang, but it's not a uniform expansion. Different regions of the universe are expanding at different rates. By examining the distribution of hydrogen in the Lyman alpha forest, astronomers are piecing together a timeline that chronicles how matter and energy have interacted over billions of years. By mapping the density of the hydrogen gas, we can learn about the changes in the expansion rate of the universe over time. This directly ties into the concept of dark energy, the mysterious force thought to be responsible for the accelerated expansion of the universe. Understanding how the Lyman alpha forest interacts with the expansion of space itself could reveal crucial insights about this enigmatic force. The scale of the Lyman alpha forest is as staggering as the mysteries it holds. When looking at the light from distant quasars, we are not just observing individual absorption lines but rather a continuous, vast forest of them that spans hundreds of millions of light years. This forest covers enormous stretches of the universe, serving as a record of hydrogen gas present in intergalactic space over cosmic history. Each absorption feature is a snapshot in time, and when combined, they form a detailed map of the intergalactic medium as it was in the past. One of the more exciting prospects of this research is how it could allow us to study regions of space that are too distant to be explored by traditional means. For instance, the Lyman alpha forest enables us to study gas clouds far beyond the reach of even the most powerful telescopes. This is possible because of the way quasar light interacts with the intergalactic medium. The light from quasars, though incredibly distant, travels for billions of years and passes through vast stretches of intergalactic space, providing a direct look at the matter that lies between galaxies. This allows astronomers to peer into the empty space between galaxies and uncover a wealth of information that would otherwise be invisible. One of the most significant breakthroughs in our understanding of the Lyman alpha forest came in the 1990s, when astronomers began using large-scale surveys to catalog and analyze the absorption lines more systematically. This marked a pivotal moment in the study of the intergalactic medium. By cataloging thousands of absorption lines, astronomers were able to construct the first detailed map of hydrogen in the universe, a map that continues to expand as new surveys and observations are made. This work was instrumental in revealing the structure of the intergalactic medium, which had previously been an enigma. The structure of the Lyman alpha forest, with its dense pockets of hydrogen gas and vast, empty voids, provides an intriguing glimpse into the dynamic, ever-changing state of the universe. The Lyman alpha forest has also played a key role in enhancing our understanding of the large-scale structure of the universe. The presence of these absorption lines reveals the web-like distribution of matter in the universe. The vast filaments of hydrogen gas that stretch across the cosmic landscape correspond to the large-scale structures known as the cosmic web. This cosmic web, composed of dark matter, gas, and galaxies, serves as the skeleton of the universe, dictating how galaxies and clusters form and evolve. Understanding the precise way in which the Lyman alpha forest traces this web helps us to further understand the evolution of the cosmos as a whole. It is through studying the large-scale structure of the universe that we can gain insight into the processes of galaxy formation and the influence of dark matter on the development of cosmic structures. The connection between the Lyman alpha forest and dark matter is another key avenue of research. Although dark matter cannot be directly observed, its presence is inferred by its gravitational effects on visible matter. By examining the way the absorption lines in the Lyman alpha forest are affected by dark matter, we can uncover more about its distribution and behavior across the universe. Dark matter is thought to be present in vast quantities, influencing the formation of galaxies, galaxy clusters, and the structure of the universe itself. The Lyman alpha forest is a powerful tool in mapping out the distribution of this mysterious substance, providing clues about how dark matter has shaped the large-scale structures we observe today. In many ways, the Lyman alpha forest acts as a time machine, offering a window into the distant past of the universe. The light from quasars, which can take billions of years to reach us, carries information from epochs long past. By analyzing the absorption lines in this light, we are able to piece together the evolution of the universe over cosmic timescales. The forest of hydrogen absorption lines reveals the changes in the intergalactic medium, the effects of cosmic reionization, the formation of galaxies, and the intricate dance between matter and energy that has shaped the universe as we know it. As we study these absorption lines, we are not just observing a snapshot of the universe. We are witnessing a cosmic story unfolding across vast distances and times. One of the most intriguing aspects of the Lyman alpha forest is its potential to answer some of the deepest questions about the universe's origin. The study of these absorption lines is closely tied to the phenomenon of cosmic reionization, which occurred roughly 13 billion years ago. During this period, the universe transitioned from being opaque to transparent as hydrogen gas was ionized by the first stars and galaxies. This process allowed light to travel freely, shaping the structure of the universe and giving rise to the stars, galaxies, and other cosmic structures we observe today. The absorption lines in the Lyman alpha forest are a direct consequence of this ionization, and by studying these lines, scientists can gain a better understanding of when and how reionization occurred, offering valuable insights into the early universe. As our understanding of the Lyman alpha forest deepens, it also presents new questions and challenges. For example, the interaction between the hydrogen gas in the intergalactic medium and the radiation from quasars and galaxies is a complex and ongoing process. The study of the Lyman alpha forest requires careful consideration of how these interactions affect the absorption lines and how different types of radiation influence the gas. This is a challenging task, but one that is essential for developing a comprehensive understanding of the forest's role in cosmic evolution. As new observational techniques and computational models emerge, astronomers will continue to refine their understanding of the Lyman alpha forest and its role in the broader context of cosmology. The future of the Lyman alpha forest lies in the continued development of next-generation telescopes and computational models. Instruments like the James Webb Space Telescope, which is capable of observing the universe in the infrared spectrum, will provide a new level of detail in the study of distant quasars and their surrounding hydrogen clouds. The increased sensitivity and resolution of these telescopes will allow scientists to study the Lyman alpha forest with greater precision, uncovering new details about the intergalactic medium and the evolution of the universe. In addition to the advancements in observational technology, the ongoing development of sophisticated computer simulations will allow astronomers to model the interactions between light, hydrogen, and dark matter with unprecedented accuracy. These simulations will help to interpret the vast amount of data collected from the Lyman alpha forest, providing a deeper understanding of how cosmic structures form and evolve. As we continue to explore the mysteries of the Lyman alpha forest, we are not just uncovering new facts about the universe. We are engaging in a journey that takes us back in time to the earliest moments of the cosmos, allowing us to study the conditions that gave rise to galaxies, stars, and the very structure of the universe itself. The Lyman alpha forest is a critical tool in the quest to understand our cosmic origins, and as we probe its depths, we are uncovering some of the most profound mysteries of the universe. The study of the Lyman alpha forest has not only advanced our understanding of the universe's past but also opened up new avenues of investigation in cosmology. For instance, the absorption lines we observe in quasar spectra allow astronomers to measure the density and distribution of matter in the vast stretches of space between galaxies. By studying these absorption features, we can determine how much hydrogen exists in these regions and how it interacts with radiation. These measurements offer a rare glimpse into the empty space that exists between galaxies, which accounts for most of the universe's volume but is rarely studied in depth. Moreover, the Lyman alpha forest has provided us with one of the most effective tools to study the elusive properties of dark energy. While the exact nature of dark energy remains one of the biggest unsolved questions in physics, the way it accelerates the expansion of the universe can be observed indirectly. By studying how the intergalactic medium evolves and the way the Lyman alpha forest changes over time, astronomers can gain crucial insights into the effects of dark energy. The forest can help map out the accelerated expansion of the universe, revealing patterns that could lead to a deeper understanding of the force driving this expansion. As we zoom in closer to the phenomenon itself, the physical process of absorption lines in the Lyman alpha forest is a result of the interaction between light and hydrogen atoms. When light from a distant quasar passes through a cloud of hydrogen gas in intergalactic space, certain wavelengths of light are absorbed by the hydrogen atoms. These absorbed wavelengths correspond to the Lyman alpha transition in hydrogen, which occurs when an electron in a hydrogen atom moves from a higher energy level to the ground state. This absorption creates a dark line in the spectrum at a very specific wavelength, corresponding to the Lyman alpha radiation. These lines provide valuable information about the distance to the gas clouds and the conditions in these regions of space. What makes the Lyman alpha forest even more fascinating is the fact that it acts as a multi-layered map. While we may think of the universe as being composed mostly of galaxies, stars, and black holes, much of the space between these objects is not empty but filled with gas. These gas clouds are not easily visible to traditional telescopes because they are not luminous. However, by analyzing the absorption lines in quasar spectra, we can reveal these hidden layers of the cosmos. The density of hydrogen in these clouds provides a window into the structure and evolution of the universe. Through the Lyman alpha forest, we can map the vast, invisible web of intergalactic matter that spans the cosmos. One of the significant contributions the Lyman alpha forest has made to our understanding of the early universe is its connection to the epoch of reionization. Around 13 billion years ago, the universe underwent a dramatic shift from being opaque to transparent. During this time, the first stars and galaxies formed, and their radiation ionized the hydrogen gas that filled the universe, making it possible for light to travel freely. The study of the Lyman alpha forest is instrumental in uncovering the details of this period. The absorption lines provide clues about the state of the universe before and after reionization, offering a glimpse into how the first structures in the universe formed and how they impacted the surrounding environment. Understanding reionization through the Lyman alpha forest helps us piece together a crucial piece of cosmic history. The transition from opaque to transparent was not a smooth, uniform process. It occurred over a period of several 100 million years, and during that time, different regions of the universe ionized at different rates. By examining the variations in the absorption lines, astronomers can identify how and when different regions of the universe transition from neutral hydrogen to ionized hydrogen. These patterns are key to understanding the evolution of the cosmos, and they also provide insight into the properties of the first stars and galaxies that were responsible for this transformation. While much of the focus has been on the role of hydrogen in the Lyman alpha forest, it's also important to note that other elements and compounds contribute to the absorption lines we observe. For example, metal absorption lines, such as those caused by heavier elements like carbon, oxygen, and iron, are often present alongside the hydrogen lines. These lines provide additional layers of information about the composition and chemical evolution of the intergalactic medium. The presence of metals in the forest suggests that stars and galaxies were already enriching the surrounding gas with heavy elements at the time these absorption lines were created. This connection between the Lyman alpha forest and stellar evolution allows us to study the chemical processes that shape the universe. In addition to their significance for understanding cosmic evolution, the absorption lines in the Lyman alpha forest are essential for mapping the large-scale structure of the universe. The distribution of hydrogen gas and its relationship with dark matter and dark energy forms the backbone of the cosmic web. This web of matter, which includes galaxies, clusters, and vast voids, can be traced through the Lyman alpha forest. Understanding the distribution of hydrogen across the universe gives us critical information about the formation and clustering of galaxies, as well as the overall shape of the universe. Recent advances in observational technology have revolutionized our ability to study the Lyman alpha forest. New telescopes like the James Webb Space Telescope are capable of capturing incredibly detailed quasar spectra from far beyond what was previously possible. This new data provides unprecedented clarity in mapping the intergalactic medium, allowing scientists to refine their models of the universe's evolution. The high sensitivity of these instruments enables the detection of even fainter absorption lines, expanding the reach of our cosmic maps and pushing the boundaries of what we know about the distant universe. The implications of this research extend far beyond the Lyman alpha forest itself. By refining our understanding of the intergalactic medium, we are also improving our ability to measure other fundamental aspects of cosmology, such as the expansion rate of the universe, the distribution of dark matter, and the nature of dark energy. These are some of the most profound and unanswered questions in science. The study of the Lyman alpha forest is not just the pursuit of understanding one specific phenomenon, but a key to unlocking the broader mysteries of the universe. In many ways, the Lyman alpha forest represents the universe's hidden map, a map that, despite being invisible to the naked eye, is slowly revealing its secrets. The absorption lines act like the brushstrokes of a cosmic painting, each line representing a unique piece of the puzzle. As we continue to study the forest, we are learning not only about the hydrogen gas that fills the voids between galaxies, but also about the larger forces that govern the universe. Through this intricate web of light and matter, we gain a deeper appreciation for the complexity and beauty of the cosmos. But the Lyman alpha forest also serves as a reminder of how much we still have to learn. Despite all the progress we've made in observing the universe, there are still many questions left unanswered. How did the first stars form? What exactly happened during reionization? What is the full extent of dark energy's influence on the cosmos? As we continue to explore these questions, the Lyman alpha forest will remain a key tool in our quest for answers. It will continue to be a cosmic roadmap, guiding us through the vast and mysterious expanse of the universe. The Lyman alpha forest stands as one of the most important tools for exploring the universe's most profound mysteries. It is a record of the unseen, a map of the invisible forces that shape the cosmos, and a glimpse into the past that helps us understand how the universe has evolved. With each new discovery, we are one step closer to answering some of the biggest questions in science. As we continue to study this cosmic forest, we can only imagine the incredible discoveries that await us, and the deeper understanding of the universe that lies just beyond the horizon. The potential of the Lyman alpha forest as a tool in unraveling the mysteries of the cosmos is still far from exhausted. As scientists and astronomers continue to refine their techniques and instruments, the forest promises even greater insights into the structure and history of the universe. One area of particular interest is how the Lyman alpha forest may help us understand the relationship between baryonic matter and dark matter, two of the fundamental components of the cosmos. Baryonic matter, which consists of protons, neutrons, and electrons, is the ordinary matter that makes up stars, planets, and everything we observe in the universe. However, the majority of the universe's mass is believed to be in the form of dark matter, which does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Understanding the distribution and properties of both baryonic and dark matter is critical to understanding the large-scale structure of the universe and the role of gravity in shaping cosmic evolution. The Lyman alpha forest can play a pivotal role in this area of research by helping astronomers map the distribution of baryonic matter in relation to dark matter. Because the gas clouds that cause the Lyman alpha absorption lines are believed to interact with dark matter, studying how these clouds cluster and behave can provide valuable clues about the elusive dark matter. By comparing the Lyman alpha forest's map of baryonic matter with models of dark matter distribution, scientists can test hypotheses about how these two forms of matter influence each other, and how they have contributed to the formation of galaxies, galaxy clusters, and the large-scale structure of the universe. Moreover, the study of the Lyman alpha forest has practical implications for understanding the fundamental nature of the universe's expansion. Cosmologists have long debated the true cause of the accelerated expansion of the universe. While the leading theory points to dark energy as the culprit, the role of other factors, such as the distribution of matter, the rate of star formation, or even possible variations in the laws of physics, remains uncertain. By studying the way the Lyman alpha forest evolves over time, astronomers can gain insight into how the universe's expansion has affected different regions, and how the presence of matter has influenced this process. Recent advancements in computational simulations have also played a crucial role in advancing our understanding of the Lyman alpha forest. These simulations, which model the evolution of the intergalactic medium and the formation of absorption lines, are becoming increasingly sophisticated. With greater computational power, scientists can now simulate the behavior of hydrogen gas on cosmological scales and compare these simulations to real-world observations. This allows them to refine their models and make more accurate predictions about the behavior of matter in the early universe, further enhancing the utility of the Lyman alpha forest as a tool for cosmological research. In addition to its role in understanding cosmic evolution, the Lyman alpha forest also has important implications for the study of galaxy formation and evolution. The absorption lines in the forest provide a detailed map of the intergalactic medium, which is the gas-filled space between galaxies. The properties of this medium can tell us a great deal about how galaxies form and evolve. For example, the presence of certain absorption features can indicate whether galaxies have been actively forming stars or whether they have been quenched by some external process, such as feedback from supermassive black holes. The study of the Lyman alpha forest thus provides a window into the processes that shape galaxies and offers a complementary approach to studying galaxy formation alongside other techniques, such as observing galaxy surveys and simulations. The future of Lyman alpha forest research looks particularly promising due to the launch of the James Webb Space Telescope, JWST. The JWST, with its advanced capabilities for observing distant objects in the infrared, is poised to revolutionize our ability to study the Lyman alpha forest in unprecedented detail. With its ability to observe galaxies and quasars billions of light-years away, the JWST will provide us with clearer, more precise spectra of distant quasars, revealing even more intricate details about the absorption lines in the Lyman alpha forest. This will allow for more accurate mapping of the intergalactic medium and provide new insights into how the universe has evolved over time. One of the most exciting aspects of the JWST's capabilities is its ability to observe the Lyman alpha forest at earlier epochs in the universe's history. The current generation of telescopes can observe quasars and their associated absorption features from roughly 10 billion years ago, during a time when the universe was already well into the process of forming galaxies. However, the JWST will be able to peer even further back in time, to the era of the first galaxies and the earliest stages of the universe's formation. By studying the Lyman alpha forest from these early epochs, astronomers will gain a better understanding of how the first stars and galaxies formed and how their light impacted the surrounding hydrogen gas, leading to the reionization of the universe. Moreover, the ability to study the Lyman alpha forest in the infrared will allow astronomers to investigate absorption features that are obscured by the interstellar dust in the Milky Way. The Earth's atmosphere and the dust in our own galaxy have made it difficult to study distant absorption lines in the past, but the JWST's location beyond Earth's atmosphere and its advanced infrared instruments will provide unprecedented clarity in this area. This means that more distant and faint absorption features can be analyzed with much greater precision, allowing for a more detailed map of the universe's hidden structures. Along with the JWST, other future missions like the Extremely Large Telescope, ELT, and the Square Kilometer Array, SKA, are expected to play an instrumental role in advancing our understanding of the Lyman alpha forest. These ground-based observatories will provide complementary insights into the absorption lines, helping to fill in the gaps left by space-based telescopes. With their incredible resolution and sensitivity, these observatories will allow scientists to study the Lyman alpha forest with greater detail and accuracy than ever before. While the study of the Lyman alpha forest may seem niche, its broader implications for cosmology and astrophysics are profound. By analyzing the absorption lines in the spectra of distant quasars, we are not only learning about the hydrogen gas that fills the universe but also uncovering crucial information about dark matter, dark energy, the evolution of galaxies, and the very nature of the universe itself. The Lyman alpha forest is a powerful tool that continues to reveal the hidden layers of the cosmos, providing us with a deeper understanding of the universe's past, present, and future. As astronomers and scientists continue to refine their models and tools, the Lyman alpha forest will undoubtedly remain a key player in the ongoing effort to answer some of the most profound questions in science. What is the nature of dark matter? How did the first galaxies form? What happened during the epoch of reionization? And most intriguingly, how does the universe continue to evolve? With each new breakthrough in Lyman alpha forest research, we move one step closer to unraveling the mysteries of the cosmos. In the grand scheme of the universe, the Lyman alpha forest serves as a reminder that even the most invisible and overlooked aspects of the cosmos can yield profound insights. It may be hidden in the darkness between galaxies, but it is precisely through this darkness that we find the clues to the universe's deepest secrets. As our tools and techniques improve, the Lyman alpha forest will continue to illuminate the unknown, guiding us toward a greater understanding of the universe and our place within it. As we continue to explore the mysteries of the Lyman alpha forest, it becomes clear that this hidden map of the universe is not just a tool for astronomers but also a testament to the incredible complexity and interconnectedness of the cosmos. The more we study the absorption lines created by hydrogen, the more we realize that this seemingly simple phenomenon holds the keys to understanding the universe on scales both vast and minute. One of the most fascinating aspects of the Lyman alpha forest is its potential to shed light on the process known as cosmic reionization. This was a pivotal period in the history of the universe, occurring roughly 1 billion years after the Big Bang, when the first stars and galaxies began to form. The ultraviolet light from these early stars and galaxies ionized the surrounding hydrogen gas, effectively reigniting the universe and transforming it from a neutral state into an ionized one. Understanding the precise details of this process is critical for understanding how the universe transitioned from the cosmic dark ages to the more structured and complex universe we observe today. By studying the Lyman alpha forest, astronomers can trace the remnants of this cosmic reionization. The absorption features in the spectra of distant quasars provide a snapshot of the hydrogen gas present during the era of reionization, revealing how it was distributed throughout the universe. This data helps astronomers pinpoint when reionization occurred and how the light from the first stars and galaxies spread across the universe. Understanding this process not only provides insight into the early history of the universe but also has profound implications for how galaxies form and evolve. In addition to its role in studying reionization, the Lyman alpha forest is also a powerful tool for exploring the large-scale structure of the universe. The distribution of absorption lines across the sky reveals the cosmic web, a vast network of galaxies, gas, and dark matter that forms the skeleton of the universe. The Lyman alpha forest acts as a tracer for this cosmic web, allowing astronomers to map out how galaxies and gas are distributed across vast distances. This map, when combined with data from galaxy surveys and other observational techniques, gives us a much more complete picture of the universe's large-scale structure. Interestingly, the study of the Lyman alpha forest is also helping to challenge and refine our models of the universe. For decades, cosmologists have relied on the lambda cold dark matter, lambda CDM, model to explain the formation and evolution of the universe. This model suggests that the universe began with the Big Bang, expanded rapidly in its early moments, and has continued to evolve under the influence of dark matter and dark energy. While this model has been successful in explaining many observed phenomena, there are still gaps in our understanding, particularly when it comes to the distribution of matter in the universe. The Lyman alpha forest is helping to fill in some of these gaps by providing a direct measurement of the intergalactic medium. Unlike other methods of studying the cosmos, which rely on indirect measurements of galaxy light or cosmic microwave background radiation, the Lyman alpha forest provides a real-time snapshot of the gas between galaxies. This allows astronomers to refine their models of cosmic evolution and test the assumptions of the lambda CDM model. By comparing observations of the Lyman alpha forest with the predictions of these models, scientists can evaluate their accuracy and adjust them as needed, leading to a more accurate understanding of the universe's history. Moreover, the Lyman alpha forest provides insights into the physics of hydrogen gas itself. Hydrogen is the most abundant element in the universe, and its behavior at various temperatures and densities can reveal a great deal about the physical processes that govern the cosmos. The absorption lines created by hydrogen atoms in the intergalactic medium offer a direct view of how hydrogen interacts with light, how it behaves under different conditions, and how it has evolved over billions of years. This knowledge not only helps astronomers understand the intergalactic medium but also provides fundamental insights into the properties of matter itself. In recent years, there has been growing interest in the role of the Lyman alpha forest in the search for extraterrestrial life. While the absorption lines created by hydrogen do not directly tell us about life beyond Earth, they can provide valuable information about the conditions necessary for life to arise. For instance, by studying the chemical composition of the intergalactic medium and the way that light interacts with it, scientists can gain insight into the prevalence of the building blocks of life, such as carbon, oxygen, and nitrogen, across the universe. Additionally, the conditions observed in the Lyman alpha forest may offer clues about the habitability of exoplanets, the search for biosignatures, and the overall potential for life to exist in other parts of the universe. The Lyman alpha forest is also being used to investigate other intriguing cosmic phenomena, such as the possible existence of exotic particles. While the majority of the absorption features we observe in the forest can be explained by the known physics of hydrogen, some scientists believe that certain anomalies in the Lyman alpha forest might be a sign of new, yet to be discovered particles. These particles could potentially be related to dark matter, dark energy, or other fundamental forces of nature. By analyzing the Lyman alpha forest for signs of such anomalies, astronomers could make groundbreaking discoveries that change our understanding of particle physics and cosmology. In the near future, the ongoing development of advanced instruments and techniques will undoubtedly expand our ability to study the Lyman alpha forest. Instruments like the James Webb Space Telescope, the Extremely Large Telescope, and the Square Kilometre Array are poised to provide more detailed and comprehensive data than ever before. These telescopes will enable us to observe even more distant quasars and their associated absorption lines, allowing for a more precise map of the intergalactic medium. With greater sensitivity, these instruments will also be able to detect more subtle features in the Lyman alpha forest, potentially revealing new insights into the structure and evolution of the universe. One particularly exciting development in the field of Lyman alpha forest research is the application of artificial intelligence, AI, and machine learning, ML, to analyze the massive amounts of data generated by these observations. AI and ML algorithms can help identify patterns and correlations in the data that might be difficult for human researchers to detect. For example, these techniques can be used to analyze the distribution of absorption lines, study the relationship between the forest and the cosmic web, and identify unusual features that might indicate new physical phenomena. As AI and ML continue to evolve, they will play an increasingly important role in unlocking the secrets of the Lyman alpha forest. The study of the Lyman alpha forest is still in its early stages, and there is no telling how much more we can learn from this fascinating feature of the universe. But one thing is clear: as we continue to explore the Lyman alpha forest, we are uncovering a hidden map of the universe that reveals the intricate structure of the cosmos, the history of its evolution, and the mysteries that lie at the heart of its existence. From the role of hydrogen in the early universe to the search for dark matter and exotic particles, the Lyman alpha forest is helping us answer some of the most profound questions in science. As technology advances and our understanding of the universe deepens, we are sure to learn even more about this cosmic forest and the secrets it holds. It may be invisible to the naked eye, but the Lyman alpha forest remains one of the most powerful tools we have for exploring the distant reaches of the universe and unlocking the mysteries of the cosmos. By studying this hidden map, we are not only learning about the universe's past but also gaining insights that will shape our understanding of its future. As we continue our journey through the mysteries of the Lyman alpha forest, it's important to acknowledge the sheer scale of what we are observing. Each absorption line in the spectra of distant quasars represents a tiny sliver of a much larger cosmic story. This forest of absorption features stretches across vast regions of space, revealing a complex tapestry of gas, galaxies, and the unseen matter that shapes the universe. In fact, the Lyman alpha forest holds particular significance for cosmologists studying the distribution of dark matter, the mysterious and invisible substance that makes up about 85% of the matter in the universe. Dark matter doesn't emit light or radiation, making it invisible to conventional telescopes. However, its presence can be inferred by its gravitational effects on visible matter. The way that hydrogen in the intergalactic medium interacts with the light from distant quasars provides a sort of shadow of dark matter's influence. This has led scientists to propose that the distribution of hydrogen, as seen in the Lyman alpha forest, could provide indirect evidence of where dark matter is located. For example, when astronomers study the absorption lines in the Lyman alpha forest, they can look for patterns that might indicate the presence of dark matter clumps. These clumps, also known as dark matter halos, are thought to be the gravitational scaffolding around which galaxies and clusters of galaxies form. By comparing the distribution of absorption features to our theoretical models of dark matter, we can learn more about how dark matter shapes the structure of the universe. In a sense, the Lyman alpha forest acts as a cosmic map of the invisible universe. Just as a traditional map can show us the locations of cities, mountains, and rivers, the Lyman alpha forest shows us where the gas, and by extension, the dark matter, is located. This information is invaluable for cosmologists working to refine our understanding of the universe's composition and structure. As we dive deeper into the Lyman alpha forest's implications, one of the most intriguing questions is how it could be used to study the future of the universe. The absorption lines we observe today were created billions of years ago, but they can still tell us a great deal about the current state of the universe. In particular, these absorption lines can provide insight into the expansion of the universe. The universe is not static, it is constantly stretching and evolving, and understanding how this expansion affects the intergalactic medium is key to understanding the fate of the cosmos. The study of the Lyman alpha forest is crucial for our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy is one of the biggest puzzles in modern cosmology, and it's only by gathering more data on the Lyman alpha forest and its associated absorption features that we can hope to uncover its secrets. By studying the way that absorption lines evolve over time and how they relate to the large-scale structure of the universe, scientists can learn more about how dark energy is influencing the cosmic expansion. This knowledge will be essential in predicting the future of the universe, including whether it will continue expanding indefinitely or whether it might eventually slow down or even reverse its expansion. Moreover, understanding the Lyman alpha forests provides valuable insights into galaxy formation. The intergalactic medium, made up largely of hydrogen gas, is the raw material from which galaxies are built. As gas flows into the gravitational wells of dark matter halos, it forms the stars, gas clouds, and galaxies that we observe today. The absorption lines in the Lyman alpha forest act as a fossil record of this process, offering a glimpse into the early stages of galaxy formation. By analyzing the distribution of hydrogen gas along the line of sight to distant quasars, astronomers can trace how gas has flowed and accumulated to form galaxies over billions of years. The more we study the Lyman alpha forest, the more we realize that it holds not only the keys to the past but also to the future. As our tools and methods for analyzing these absorption lines improve, we will continue to unlock new chapters in the story of the universe's evolution. The Lyman alpha forest is an ongoing mystery, one that continues to reveal new insights about the universe's origins, its present state, and its eventual fate. As astronomers refine their understanding of the Lyman alpha forest, they are also developing new ways to visualize and interpret the data. The process of interpreting the Lyman alpha forest is complex, requiring sophisticated techniques to separate the various absorption lines from each other and to account for the effects of redshift, which occurs as light stretches over vast distances. Redshift causes light from distant objects to shift toward longer wavelengths, which in turn stretches the absorption features in the Lyman alpha forest. To make sense of these features, astronomers must employ intricate mathematical models and simulations that account for both the observed data and the theoretical understanding of how hydrogen behaves under various conditions. To help interpret this data, astronomers have turned to cutting-edge computational techniques, such as machine learning and artificial intelligence. These tools can help identify patterns in the vast amounts of data generated by spectroscopic surveys, allowing researchers to extract meaningful insights more efficiently than ever before. For instance, machine learning algorithms can be used to classify different types of absorption features, analyze the structure of the Lyman alpha forest, and identify unusual anomalies that might indicate new physical phenomena. This is a rapidly growing area of research, and it's likely that in the coming years, artificial intelligence will play an increasingly important role in decoding the mysteries of the Lyman alpha forest. Another exciting avenue of research involves the development of next-generation telescopes, such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT. These advanced instruments will provide unparalleled sensitivity and resolution, allowing astronomers to observe more distant quasars and detect more subtle features in the Lyman alpha forest. The JWST, for instance, is expected to revolutionize our understanding of the early universe by allowing us to observe the first galaxies and the hydrogen gas surrounding them. The data collected by these telescopes will provide an even clearer picture of the intergalactic medium, offering new insights into the processes that shape the universe. As we continue to explore the Lyman alpha forest and its secrets, it's important to keep in mind the broader implications of this research. The study of the intergalactic medium is not just about understanding the past or the present, it's about gaining a deeper appreciation for the intricate and interconnected nature of the universe. Each absorption line, each faint trace of hydrogen, is a clue that helps us piece together the cosmic puzzle. Through the study of the Lyman alpha forest, we are uncovering a hidden map of the universe that reveals not only the distribution of matter but also the processes that govern its evolution. This map is far from complete, but each discovery brings us one step closer to understanding the vast and mysterious cosmos in which we live. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.